I would pay very close attention to this one. If I was to write a test question, I couldn't write one that's better than the start to this question. Just letting you know that I would add stuff to it, and I'm going to be very clear in a few moments what I would add to it. So this might be an excellent place for you to kind of jot some notes down, more than just what's the answer to the question. So I want you to imagine this air table, and I'm going to draw the air table twice so that we have two different versions of it, I guess. On one of them, we're told that there's I think they call it a puck, is that right? Or a disc. And it's 2 kilograms, and it is on a string that is 1/2 meter long, and it's rotating with an angular speed of 2 radians per second. Does that make sense? And does that describe what's in the problem? Right. Now, do you guys remember the lab where we spun the mass above our heads and held onto the string, or held onto the tube and pulled the string? You guys remember that lab? And we were measuring G with that lab, and it was about centripetal acceleration. But you should remember that when you pulled on the string, the thing spun faster. That's conservation of angular momentum. I mean, you thought it's because you're pulling on the string and shortening it, but it's also conservation of angular momentum, which is what's happening in this problem. As you pull on the string and you shorten the distance to the center, you are changing the moment of inertia of the disk. Now, this is the part that's hard to understand, so you guys who are not always able to follow me because I talk too fast or something, I want to remind you that moment of inertia is a measure of how far the mass is from the axis of rotation. In this case, our disk is a point mass. Now, you may not have written this down, but a point mass, which is a single object rotating about some axis, has a moment of inertia of mr squared. Anytime an object is rotating around some point outside the object, anytime, you would use the moment of inertia of a point mass. Do I need to say that again, or do you guys have that down in your notes? I would encourage you to write it down. Anytime an object is rotating about some point that is outside of the object, then you would treat the object as a point mass. We only have to use those moments of inertia for rigid objects if their shape somehow has something to do with their inertia. But once you're rotating far away from that axis, the shape doesn't have anything to do with it anymore. So again, if you're rotating about a point outside the object, then you use the point mass. This means there's a before moment of inertia and an after moment of inertia. The before moment of inertia is the 2 kilograms rotated a distance of 0.5 meters from the axis of rotation. This is a moment of inertia of 0.5 kilograms meters squared. Afterwards, you shorten the string. The mass hasn't changed, but the string has gotten shorter. So the moment of inertia is now going to be 0.08 kilogram meter squared. It's a pretty substantial change in the moment of inertia. Now, momentum is a conserved quantity. That means that the angular momentum of the puck before you pull the string has to be equal to the angular momentum of the puck after you pull on the string. So I should use consistency. So let's say before and after. There. Before and after. That means the moment of inertia before times omega before equals moment of inertia after times omega after. Again, this is another example of the ice skater problem, where we change our moment of inertia and thus change our speed. So the puck had a moment of inertia of 0.5 and a speed of 2 radians per second. As you pull on the string, you reduce the moment of inertia to 0.08. The angular speed has to increase in order to compensate. That's it. That is this question. Find the speed afterwards. The speed afterwards is going to be 1 divided by 0.08, which I believe is 12.5 radians per second. Pretty healthy increase. From 2 radians per second to 12 radians per second. Any questions to this point? If this were the test, this would have been question A and question B. I would have been a little bit more directed as to what I would have wanted. I would have said in question A, what is the change in the moment of inertia of the system when you pull the string to 0.2 meters? And then question B, what is the change in the angular speed of the system? So I would have broken it up into 2 parts. Now, your question goes on to ask about the linear speed of the objects, which we could find real quick. Since we have the 2 angular speeds, the linear speed before is the angular speed times the radius, or 2 radians per second times 0.5 meters. So that's 1 meter per second for our linear speed before. Our linear speed after is going to be the angular speed after times the new radius. That's going to be 12.5 times 0.2, which is a linear speed of 2.5. So it's a pretty substantial change. Now, I probably wouldn't ask that question. It's unlikely. I want to focus on the rotational stuff. I would, however, let's look at this. My question E would be to substantially change this and ask the question that most of you aren't thinking about, but your job is trying to anticipate what I would ask, which is compare the tension in the string. That's what I would likely to ask. Compare the tension in the string before to the tension after, which will throw some of you for a loop. That's why it would be like worth fewer points. But if you want an A, you'd have to realize that the tension is a centripetal force, which equals either mv squared over r, or now m omega squared times r. Either one of those is one you could do. We've talked about both. You should be able to compare the 2 tensions. This comes from the tension. It's the tension that does work on the system, by the way. That's the force that does the work. So we have all the information to do that. The first one would be the before tension, would be 2 times 1 squared divided by 0.5, compared with the tension after, which would be 2 times 2.5 squared divided by 0.2. Meaning it takes more tension to pull that string and make the radius smaller. So, for those of you who need it spelled out more clearly, this problem conserved momentum, but did not conserve energy. Energy was added to the system by you when you pulled on the string. You tend to miss the ability to assemble a paragraph like that. But that kind of paragraph is what I will be asking on the test. I'll ask something like, where did the energy come from? And if you make it this far into the problem, you'd have to recognize that the energy came from the tension that you pulling on the string added energy to the system. All right. So I've given you a clear idea of how I'm going to ask this on the test. Ask this question. And just a quick reminder, the moment of inertia before was 0.5, and the moment of inertia after was 0.08. And the angular speed before was 2, and the angular speed after was 12.5. I would probably follow this question up with a question C or D, probably C, which would be, what is the change in kinetic energy of the system? That's probably what I would ask next. But I probably wouldn't ask it that way. What I would probably ask instead is how much work was done on the puck when you pulled on the string. That's what I'm likely to ask, and that's designed to be tricky. But they are the same question. You guys don't tend to pay attention close, so I'll remind you that any time you do work, you change something's energy. You pulling on the string is what causes this change in energy. So, if we look at C, although momentum is conserved, energy is not. And that might not be clear. So C asks, what's the change in kinetic energy? The change in kinetic energy is 1/2 I after, omega after squared, minus 1/2 I before, omega before squared. That's going to be 1/2 times 0.08 times 12.5 squared minus 1/2 times 0.5 times 2 squared. Now you guys who are super smart, you could also do 1/2 mv squared minus 1/2 mv squared. Since we calculated the linear velocity, you could do it this way. The mass never changed though, but the linear velocity changed a lot. So this would be 1/2 times 2 times 2.5 squared minus 1/2 times 2 times 1 squared. This will give you the same answer. It doesn't matter which one you do. I am likely to not ask about the linear velocity, which makes this one a more likely scenario. Either way, somebody probably has the answer for me. If not, I'm not going to sit here and wait for you guys to push buttons. I am going to say that D, which is how much work is done, by pulling on a string, it would be whatever this answer is. You guys understand that that's not new material, but it's confusing for a bunch of you. Any questions about this? Yes, sir?
So if you were to ask it, C and D would have
C and D would have the same answer. Yep. Now, I could envision question E. Just so you guys know, I have lots of vision. Just a quick sketch before I answer the next question. This would be my rendition of a of the merry-go-round. So if I have the children's merry-go-round at the at a playground, if I tell you that this merry-go-round has a moment of inertia of 800 kilogram meters squared, but that there are 4 kids standing at the edge, each of mass 50, located 2 meters from the edge. Could you tell me the moment of inertia of the system? I'm not sure you can. Just asking if you can. The 4 people would be point masses. They would have moments of inertia of simply mr squared, which would be 50 times 2 squared. So each person adds, 200 kilogram meter squared. So the moment of inertia of the system would be 800 plus 4 times 200, or 1600. Now you're asking, of course, why I would bother with this example. I want you to think about what you just did. If each of these people walks to the center, what does that do to the moment of inertia? Changes isn't going to be enough, whoever said that, but increase or decrease is probably going to be an appropriate response. Does the moment of inertia get bigger or smaller as objects move towards the center? Smaller. So if this moment of inertia decreases, what has to happen to the spin of the merry-go-round? So now you know what your test question is going to be, right? I mean, it's the same problem as the puck on the string. You would be thrown because you guys tend to not be able to extrapolate to new situations. That's a new situation. What if instead it's a space station? You know, a space station that has a ring in the center, and the people can either be on this part of the ring, or they can move to this part of the ring. If there's 100 people and they all move to the inside ring, does the moment of inertia increase or decrease? If they all move to the inside of the ring, the moment of inertia would decrease. So the space station would start to spin faster. Yeah, I'm just changing the problem little bits at a time, but it's all the same problem. All right. Another question? Yes, ma'am.
A unit fire escape for a 3-story house is shown in the figure. A 30-kilogram child grabs a rope wrapped around a heavy flywheel outside a bedroom window. The flywheel is a 0.4-meter radius uniform disc with a mass of 120 kilograms. And then A is make a force diagram for the child as it moves downward at increasing speed, and another for the flywheel as it turns faster and faster. B is use Newton's second law for translational motion and the child force diagram to obtain an expression related to force that the rope exerts on him and its acceleration.
All right, I'm expecting that the flywheel is experiencing 3 forces. There's the child acting on its edge, there's the weight of the flywheel, And then there's something, I guess tension or normal force holding the flywheel from falling. It's mounted to the roof of the building. The kid is experiencing two forces, his weight downwards and tension upwards. So I'd expect you to be able to draw that free body diagram for sure. What's the next question about it?
Use Newton's second law for translational motion in the child force diagram to obtain an expression related to the force that the rope exerts on him and his acceleration.
There we go. There are three forces acting on the child. There are two forces acting on the child that the sum equal ma. So that's answer B.
That was all I had for questions.
All right, I will ask more than this. I will ask question C. What is the net torque about the flywheel? Which will be going to be RT times I alpha. I am probably going to ask a question that requires that you solve for A, the acceleration of the child, which means that you'll have to do A equals alpha times R. And we've done this problem. This is the toilet paper problem. This is in your notes. And then I would make you take all three of these and give me an A equals. All right. I think we'll have a quiz first few minutes of class tomorrow. It is likely to focus on momentum and energy.